So, you guys in Neomed can nod if you can see the slides. Okay, super. So today I'm going to talk about the what I call the psychotropic activity of fatty acids. I'm interested in, well, the background for this is that probably like all of you, I tend to see many patients with clinical problems that are not fully resolved with what the textbooks say one should use. And there are, of course, many conditions, for example, mood dysregulation in borderline personality, for which we don't really have any approved treatments. So I have a long time hobby of going to the medical literature and asking, tell me something I don't know. And fatty acids keep coming up as potential involved entities or potential contributing factors towards solution of various clinical problems. So I wanted to share a little bit today about what I've learned along the way. So just for review, we're going to talk about fatty acids. So here is a structural formula for a fatty acid. You'll see in the center, it has a long hydrocarbon tail, so just a long chain of carbons. Usually we started at about 18 or 16 carbons in order to call it a fatty acid. And those carbon chains can extend out to about 24 carbon chains. So those are the ones that the body tends to use. And on the right of this illustration is a carboxylic acid group, so a carbon attached to two oxygens in a special kind of way. That forms a molecule that has very interesting physical properties. The long tail is hydrophobic. In other words, it is oily. It repels water, whereas the head group, the carboxylic acid, loves water. It's hydrophilic, and it can interact with aqueous substrates. So when you have that, you have the recipe for a cell membrane, and cell membranes are the building block. The majority of the cell membrane is composed of fatty acids, which are packaged into phospholipids. And so for review, phospholipid structure is like this. You see on the left two fatty acid molecules, and the body can insert whatever it needs or whatever it can find. So whether it's a 16 carbon or a 24 carbon or whatever fatty acid, they can go into those first two positions on the glycerol backbone. And then the third position, glycerol is a chain of 3 carbon atoms. And on the third position, that carbon atom will be bound to a phosphate group and then some kind of alcohol like serine or choline or something like that. So that's the structure of phospholipid. And so the body uses these phospholipids, packs them into membrane. Oh, I'm sorry, I got ahead of myself. One other note about the fatty acids is that they have these terms: saturated, monounsaturated, or polyunsaturated. When a fatty acid is saturated, that means that every single carbon is carrying the maximum possible number of hydrogen atoms attached to it. So it is saturated with hydrogen, is what that saturation refers to. Carbon can, of course, exist in double bonds with itself and actually triple bonds with itself, although those are irrelevant to fatty acids. But when a carbon in the carbon chain is double bonded to another carbon atom, that means you can't pack hydrogen onto as many hydrogens onto that. So if there's one double bond, we call that fatty acid monounsaturated because there's one point of unsaturation in the carbon chain. And if there are multiple double bonds in the carbon chain, we call those polyunsaturated. And then you'll hear about this omega number. So omega-3 or omega-6 are the most popular or most well-known kinds of fatty acids. There's also an omega-9 family that the body uses. And the number refers to how many carbons from the tail does the first double bond occur. So in omega-3 fatty acids, the first double bond will occur at carbon number 3, counting up from the tail. Or in this example on the screen, this would be an omega-6 fatty acid. So we can count 1, 2, 3, 4, 5, 6 carbon atoms from the tail at the first double bond. That's a omega-6 fatty acid. So just to clarify those terms. So I mentioned that the fatty acids are major constituents of phospholipids, and phospholipids are major constituents of cell membranes. Here we see a schematic diagram of how it works. So you have one layer of phospholipids facing the outside world from the cell's point of view. And on the other side, you have another layer of phospholipids facing the inside of the cell's world. Both the outer and the inner world are aqueous, and the middle is fatty. So this forms the water-type barrier that keeps cells separated from each other. These things move, these fatty acids, these phospholipids move around all the time inside of cell membranes. And if they're tightly packed, in other words, on the bottom right, if all the fatty acids are straight saturated hydrocarbons, then the molecules are packed very tightly and the membrane becomes viscous. Think about butter, for example, would be an example of a fat that has a lot of saturated fatty acids in it. Contrast your vision of butter with, say, your vision of canola oil or olive oil. These oils have unsaturated elements in their fatty acids, and they don't pack as tightly, so they're more fluid. And that is an important consideration because the other thing about cell membranes, as you know, they have proteins in them. Every single protein that transduces a signal from a neurotransmitter lives in the cell membrane. The thing, a target of serotonin reuptake inhibitor drugs, the serotonin transport protein, that lives in the membrane. Most all of the important proteins that mediate neurotransmitter signals and that, in fact, are the target of most of our drugs in psychiatry live in the cell membrane. And these proteins ultimately do their job by changing their shape. If you will, they wiggle. So when say a nicotinic acetylcholine receptor binds to acetylcholine, that protein literally rotates within itself and opens up a channel to allow sodium to fall inside and depolarize the neuron. If you want to take the example of a muscarinic acetylcholine receptor, that receptor protein binds to acetylcholine and changes its shape, and then turns on a G protein that helps transduce the signal to the inside of the cell. The central point here is that these proteins work by changing their shape, and the ability of the protein to change its shape is going to be highly influenced by the viscosity or the fluidity of the fats in the phospholipids that surround it. So a cell that has overrepresentation of saturated fatty acids is going to be less fluid, more hard, and those proteins are going to have a harder time moving around. That will translate into reducing the efficiency of neurotransmitter signaling. So, and I'll show you a little bit of data that says that there are some impressive correlations between fatty acid content, presumably in the cell membrane. Well, fatty acid content in cell membrane changes neurotransmitter efficiency. I don't have slides for exactly that concept, but I will show you slides that show that there's relationships between fatty acid intake and psychiatric symptoms. The beauty of the phospholipid hypotheses is that a single family of defects that affect fatty acid composition can explain a wide number of global defects in brain function. So, a relatively seemingly trivial change in fluidity can affect the efficiency of serotonin, dopamine, norepinephrine, a variety of symptoms. And so it can be, the beauty of the hypothesis is that it ties a lot of information together. One other terminology, you'll hear about essential fatty acids, and just like essential amino acids, the word essential means that we human beings or we mammals are unable to make them on our own. So we are obligated to acquire them from our diet. So mammals do not have the capacity to turn a saturated fatty acid into an omega-3 or an omega-6 family of fatty acids. We have to get omega-3 or omega-6 substrates from our diet. If we have one, precursor of an omega-3 series of an omega-3 fatty acid, we can elongate it and change it, and our bodies can work from that, but we can't just create that de novo. And if we don't get these sufficient quantities of essential fatty acids from the diet, when the cells have to make their membranes, they'll just pack it with whatever they can find handy. So that will have some deleterious effects. And I think that if you look at the second set of bullet points, the neurological or neuropsychiatric importance of the essential fatty acids is evident in these numbers. If you take out all the water, then 1/3 of the weight of your brain is fatty acids, essential fatty acids, by the way. And of those, 4, 2 in the omega-3 family, EPA and DHA, and 2 from the omega-6 family, arachidonic acid and dihomogamma-linoleic acid, we'll call it DGLA, they comprise 90% of all the fatty acid weight. In the synaptic, if you can actually neurochemically isolate the synapses, the part where neurotransmitters are released, and if you look at synaptic membrane, you'll find that DHA comprises, I believe it's 70% of the weight of fatty acids in that specialized part of the membrane. So, that just some data to speak to the importance. And this, I guess, reiterates what I've already told you. When we don't have adequate intake, or if we have genetically determined processes that over-metabolize certain essential fatty acids in the membrane, you'll wind up with deficits, and your body will put in whatever else it can find. These fatty acids also, in addition to being membrane fluidity components, the body actually does 2 functions with them. It turns them into the sources of signaling molecules. So this DGLA type of fatty acid, it gets converted. Processes exist whereby that can be taken out of cell membranes and turned into prostaglandins of the 1 series. Arachidonic acid, the most important of the omega-6 fatty acids, gets converted into the prostaglandin 2, which has a lot of signaling importance. We think about the 2 series prostaglandins as pain and inflammation modulators, but they have various functions according to what particular part of the body you're looking at. And also, interestingly, arachidonic acid is the substrate for this signaling molecule called anandamide. Anandamide is what triggers or turns on the cannabinoid receptors in our brain. So anandamide is our endogenous THC. Well, not quite that. It's our endogenous cannabinoid. And when people smoke marijuana for THC content, they are replacing their anandamide to stimulate the cannabinoid receptors. So interesting fact there. And the omega-3 fatty acids are turned into 3 series prostaglandin. And there are case reports across the decades which show that certain people can take aspirin or nonsteroidal anti-inflammatory drugs, which, as a reminder, inhibit the conversion of arachidonic acid into 2 series prostaglandins. The 2 series or the arachidonic acid can also impact dopamine signaling. So when you change the dopamine signal, you have the possibility of creating psychosis or antipsychosis, depending upon which direction it goes. And there are reports that NSAIDs can both alleviate psychotic symptoms when used as adjunctive treatments, but apparently some people are sensitive to these things, and there are numerous reports of NSAIDs actually provoking de novo psychosis. And DHA, by a more complicated set of interactions, can have primary effects on serotonin signaling. So again, they're well positioned to have multiple relevances to neurochemical function, both by changing the efficiency of the cell membrane proteins involved in neurotransmission, and by their virtue of being substances which themselves can trigger inflammation responses or other neurochemical functions that affect neurotransmitter signaling. So looking now at a handful of data, for the 15 or so minutes that I'm probably already coming close to exceeding, there's just not enough time to go over all the really amazing background and fascinating results from this. So I just want to highlight a few things. It turns out schizophrenia is relatively constant in prevalence all across the world. But the outcome, the disability resulting from schizophrenia, is not. So in some countries like Nigeria, people with schizophrenia have far less incapacitation from illness compared to countries like the United States or Denmark. I apologize, and now I realize that this graphic is really pixelated when it shows up on the slide. But this is showing you that disability rating changes across countries, and the disability rating is on the y-axis. On the x-axis, you have the ratio of dietary fat that comes from fish or vegetable sources versus from animal sources. And this graph shows that about 90% of the variability in disability from schizophrenia can be accounted for by the dietary fat intake in these various countries. Another thing about schizophrenia is that there's an enzyme called phospholipase A2. It's turned on during cell activity, and one of the jobs of phospholipase A2 is to remove fatty acids from the 2 position of the phospholipid. Usually that's occupied by arachidonic acid, and then it liberates arachidonic acid for, incorporation into various metabolic pathways. Phospholipase A2 looks like it's overactive in many cases of people with schizophrenia, and EPA, the omega-3 fatty acid at pharmacological doses, inhibits it. So I guess I'll leave it at that. So, but to point out that the overactive phospholipase A2 can create an arachidonic acid deficiency, which is something that we see when we do fatty acid studies in schizophrenia. And EPA at higher doses can inhibit or normalize that overactive enzyme, and that can explain the signal from a handful of studies that show that high dose EPA appears to have an antipsychotic effect. Speaking of the antipsychotic effect, or in this case, the psychosis preventing effect of omega-3 fatty acids, in this case, predominantly EPA, a fascinating study came out now about 10 years ago, where they took individuals that met criteria for prodromal psychosis. They weren't, they didn't have enough symptoms to merit a DSM-based diagnosis of schizophrenia, yet they had prodromal symptoms. They randomized these youth to treatment with EPA and DHA versus treatment with a oily placebo, and they found that in the middle column here, at 40 weeks of treatment, the people who were in placebo group, about a third of them converted to syndromal schizophrenia, which is par for the course in the way we currently identify prodromal states. You get about 30% predictive ability. But in the omega fatty acid treatment group, that only resulted in 5% conversion. And Eminger from Vienna and his colleagues followed up these individuals at 7-year time frame, and they found out that the placebo-treated group had progressed to about 40% conversion versus only 10% in the group that had omega-3 fatty acid treatment. And remarkably, this was for a limited time treatment. Right now I can't remember exactly. I believe it was 12 weeks. I'm blocking my... Yeah, it was 12 weeks of treatment. So relatively brief exposure to these drugs, and I'm calling them drugs now because they're functioning as such, had a striking preventive effect that apparently was even long-term. So fascinating result there. Turning to aggression, there was a study, I think this wins one of my internal prizes for extremely well-designed fatty acid study. I awarded that little award because it was well controlled placebo. It had a very strong placebo-controlled component, and it had a very unambiguous endpoint. They conducted it in prisons in the United Kingdom for about 140 days. They gave people a relatively low dose of omega-3 fatty acids supplemented with multivitamin, and they had a group that had a placebo. At the end, they asked participants to guess, were you on active treatment or placebo? And the pattern of responding was consistent with just guessing. So they were truly blinded to their treatment condition. In the British prison system, if you violate a rule, you have a hearing, and there is a presumption of innocence in the hearing, and only if clear and convincing evidence is presented of your guilt do you get adjudicated for a rule violation. So adjudicated rule violations in this presumption of innocence system was the outcome. Very unambiguous, and the results were striking. The 26% reduction in infractions in the group that had treatment with the relatively low dose fish oil plus multivitamin supplement. Very interesting. Next, let's turn our attention briefly to depression. I mentioned, for example, that DHA is strongly involved in serotonin signaling. And here we have an epidemiologic study looking at, similar to the graph I showed you with schizophrenia outcomes. In this case, it's epidemiological data looking at, on the y-axis, the prevalence of depression in various countries, and on the x-axis, the estimated fish consumption in pounds per person per year. So in Japan, I have learned today that, or relearned today, no, I learned for the first time that the average individual consumes about 150 pounds of fish in a year. But people in Japan have really low levels of depression compared to countries like West Germany or USA or Canada, which have higher rates of depression and lower rates of fish consumption. So fish is a primary source of omega-3 fatty acids, and there's that. These are data that I actually collected looking at people that were admitted to a residential treatment program. And here you see in the light gray bars, people with depressive disorders, and on the black bars, people with borderline personality. And on the x-axis, we're looking at each of the fatty acids in the omega-3 series. Here, the one that says 25 and 3, that's EPA. And on the far right, this is DHA. So you'll notice, so first of all, the people in the depression group were already substantially below national averages in omega-3 fatty acid content. So I didn't show you those data here, but everyone in the depression group was well below national average for predicted omega-3 levels. So they were bad. And comparing the borderline personality to those already deficient depressed individuals, it was remarkable. The majority of individuals with borderline personality had DHA levels that were less than the first percentile compared to a normative comparison group. So really striking deficits, a deficit exists in depression, and massive deficit in omega-3 fatty acid content and cell membranes is present in borderline personality. Meanwhile, we have these studies which get no real publicity, showing that that fatty acid treatment for borderline personality has some benefit, apparently. So in well-characterized women with bipolar disorder, with borderline personality, giving them ethyl EPA reduced measures of depression and aggression. A study looking at people coming to emergency rooms with recurrent suicidal behavior. In other words, people who had been who had had multiple ER visits for things like cutting or other forms of self-injury, when given EPA DHA supplements, perform better than placebo-treated individuals at reducing depression, suicidal thoughts, and stress tolerance. Another study from borderline personality looked at Depakote, aka divalproex, and the addition of EPA DHA had reductions of impulsivity, aggression, and self-harm. And there's another study from Amager. The last one was a spin-off of one of Amager's prodromal groups. This prodromal cohort were identified to have borderline personality symptoms, and they, when randomized to EPA DHA, had better longer-term outcomes as well. So some signal there. Altogether, then, this is really just the tip of the iceberg for arguing that the omega-3, that the fatty acids, particularly the essential ones, have inherent and significant neurochemical activity, and that what gets sold as supplements or what gets consumed in the diet actually appears to have very striking relevance to psychiatric symptoms and functioning. Unfortunately, I will come up with some, like, I'll jump into Lake Erie in the winter, I say. If anybody ever comes out and says, yes, clinicians, we, the American Psychiatric Association or the FDA or some official organization, actually makes an announcement that recognizes the medical value of these things. We don't have processes in this country or in most other countries that I'm aware of, whereby a generic drug for off-label use or natural product can have an official endorsement by a government agency to sort of then pave the way for clinicians to feel covered by the use of these drugs, or for insurance to be compelled to pay for the use of these drugs. So there's a difference between, science and government regulation. And unfortunately, in the fatty acids, we have really untapped potential in my view. So, but the good news is, they're also safe at doses of 2,000 milligrams or less. The FDA itself has categorized omega-3 fatty acids as they put it into the category called GRAS, generally regarded as safe. So there truly is very low toxicity and risk from using these at these doses, and potential high value. So the disadvantages are that there's not going to be, it's difficult to get a standardized preparation. So being over-the-counter stuff, the quality control can vary enormously, and not being officially endorsed by a government body, insurance companies are all too happy to deny payment for this. So those are some hurdles, but for those who can use them, there are potentials for benefit for our patients. So those are my thoughts on that.